I remember, said that electric field, the closed surface integral of an electric field is Q enclosed over E0, and it gives you the flux through a closed surface. And we could use Gauss's law to calculate the electric field of a sphere, whether it's an insulating sphere or a conducting sphere, and outside of the sphere and inside the sphere. So it's used for spheres. And of course, you can have a hole in the sphere like I showed you. And it's also used for cylinders inside the cylinder, right? And it could be, again, conducting cylinders. So we're basically using the cylindrical symmetry of a cylinder, spherical symmetry of a sphere. And then when you go to the outside of the cylinder, the Gauss's law works only when you're close to the cylinder, only close. So you would do a Gaussian surface. But for sphere, Gauss's law works, it doesn't matter, infinite, because spherical symmetry is the default symmetry. So Gauss's law works until infinity. But for cylinders, it only works when you are close. And then the plate symmetry is straight line symmetry. And we do Gaussian surface. So again, that only works if you're close to the plate. So close to plates. This one is close to cylinders. And anywhere inside cylinders. Anywhere inside cylinders. And by cylinders, we can also say rods. Rods or cylinders is the same thing. But spheres could be anywhere inside and anywhere outside, all the way to infinity. And outside, anywhere. So basically both inside, outside, anywhere. So it's nice to do a quick review of Gauss's law and then relate that to Amperes law. Amperes law is going to look like Gauss's law. And we have two portions for Amperes law. This one is the regular Amperes law, mu0 I enclosed. So it looks like this, except it's a line integral. The magnetic field dotted into the dl, instead of a surface integral, it's a line integral. Instead of E0 on the bottom, it's mu0 on the top. And then instead of Q, it's I, the current. Plus it's got the modified portion, mu0 E0 d phi E dt. So we'll first focus on the first portion, mu0 I0, and then I'll say what this one is all about, the second portion. Okay, so what will Gauss's law what will Amperes law be used for? Well, it also has three sets of things that we can use it for. We can use it for the current, to find the magnetic field inside of the cylinders. Let's say you have a current carrying wire, anywhere inside, it's going to create, it's a right-hand rule. So it's going to create a magnetic field that wraps around in little loops like this, inside and outside, but outside works only if you're close to the wire. So kind of like this cylinder here works anywhere inside, but when you're outside, close to the cylinder. Close to the cylinder. Same thing here. So anywhere inside and outside, but close. Outside, but close to wire. Okay. So then that Ampere's law works to find the magnetic field of that wire. The other one is a solenoid. Remember how I covered the solenoid the other day? And I said, oh, if it's an idealized solenoid, it's got a lot of wrappings and it's very long. So then the magnetic field inside is uniform. And we can find the strength of that magnetic field using Ampere's law. Okay, so on Wednesday I showed you how to find the general magnetic field with Biot-Savart law. So now we just quickly find the magnetic field using Ampere's law. The other one is a toroid. This is solenoid inside. Okay, and then the other one is toroid, which is just a solenoid wrapped in a circle, like that. So we could do these two first, because this one probably takes more time to do the outside and then the inside. And then the inside depends if it's a uniform current density, non-uniform current density. So we have more cases of this to do. So these two can go quicker. So let's do the solenoid. So you just go like this. And the idea of the Ampere's law is to decide on a loop. Instead of a Gaussian surface, we do an Amperian loop. Amperian loop, because it's a line integral. And here we do a Gaussian surface. So the Amperian loop that we do might look something like this, go like this, go out, go like this, go in, right? So let's say the length of that is L, right? And then we're going to analyze Ampere's law. And then so do the B, remember the magnetic field is a straight magnetic field. So I'm going to do B times L, right? Well, it's actually the dot product of B and L. So right, BL this way. But then when I go up, what's the dot product between the B and the L? As you're going up this way, the B is still to the right. So this one is the L vector as you're going up, and this is the B vector. You see, as you're going up until you get to the surface. Until you get to the surface. When you go outside, you're going to argue that the B field there is approximately 0. The reason why is because if it's a long solenoid, the B field is going to be forced to be trapped inside. And then it's going to curve around, then come back in. But that curvature takes a long time. So there is very little leakage of magnetic field inside the solenoid. Right outside the solenoid here. So the B field outside is 0. So when you do this dot product here, B dotted into DL, you basically just get B dotted into DL, you just get 0. So this one is just 0. And then when you go this way, back that way, the B field outside is 0 anyway. Then when you come back down, the dot product is 0 also. So then you just end up getting the B dotted into DL is just going to be B times the length. And then that's going to be equal to mu0 times the number of turns that is included within that length. So the number of turns in that length times the current enclosed. So the current enclosed from here to here essentially. And then that's it basically. And then from there, we just say mu0 N over L is the unit turn ratio. The unit turn ratio of the solenoid, which is the number of turns per unit length. And that gives you, so the other day when we did the magnetic field of a generalized solenoid, we did get the same answer. So it checks out. The other one, now let's go to the toroid. So the magnetic field of a toroid, since you're taking a solenoid and you're forcing it around the circle, like this. So the magnetic fields just look like this. So then if you do the Amperian loop this way, it's just going to be B times, and then the distance 2 pi r, right? And that's equal to the number of turns times the current mu 0 times the current enclosed. And that's it, basically. And mu 0 I over 2 pi r. It kind of looks like the equation for the magnetic field. If you remember when you had a coil, and then the magnetic field right at the center. So that one, the equation was N mu 0 I over 2r. That's a slightly different though, because that r is the radius of the coil. It doesn't have a pi, but this one does have a pi. This one is not the radius of the toroid, it's more the distance from the center of the toroid to wherever point inside the toroid. So it's, this r has a different, slightly different meaning than this r. It's the distance from the center of the wrapping of the toroid to wherever I'm trying to find the B field. So the B field on the inner edge of the toroid should be stronger than the B field at the outer edge. It's more closely wrapped here, kind of that way. Let's see here. Magnetic field of toroid. And then what we usually do to strengthen the magnetic field is we'll put an iron rod in there, you see. So we'll wrap the coil around the iron rod. That iron rod will increase the mu factor, you see, by some factor. It's kind of like putting a dielectric in a capacitor. When you put the iron rod, that strengthens the magnetic field by a certain ratio. So you see the equation, B times 2 pi r is mu ni over 2 pi r. So let's see what might be its uses. The toroid is a useful device used in everything from tape heads to tokamaks. What's a tape head? Tape motion. Tape heads for stereo cassette tapes must record on 2 tracks simultaneously. I guess we don't use these anymore, right? But I remember when I was a kid, cassette tapes, I had a whole collection. So it uses an electric current in a coil of wire produces a magnetic field similar to that of a bar magnet. And that field is much stronger if the coil has an iron-like core. So you see they put a iron core inside the coil to strengthen the field. Tape heads are made from rings of ferromagnetic material with a gap where the tape contacts it, so the magnetic field can fringe out to magnetize the emulsion on the tape. A coil of wire around the ring carries the current to produce a magnetic field proportional to the signal to be recorded. If an already magnetized tape is passed beneath the head, it can induce a voltage in the coil. Thus, the same head can be used for recording and playback. Wow, it's amazing how all this works. Oh God, there's just, everything in science is someone figured out how to use this stuff, right? So you're using this tape head, you're using a magnetic field to record the sound material on this. Then you're running it back again to actually play that sound, you know? It's crazy. Tape emulsion is uniform, but heads magnetize it in strips, enabling the recording of stereo signals. I guess they go really in depth into it, But so yeah, you could read up on that. My idea is just to sort of get your appetite wet, so you can see, oh, okay, this is what this could be used for, and then you could do your own investigation, get you interested in it. What was the other one that it said it might be used for? Tokamaks. What is that? Anyone know? Well, that's what we're here to find out, right? The tokamak, Russian tokamak, is a device which uses a powerful magnetic field to confine a hot plasma in the shape of a torus. The tokamak is one of several types of magnetic confinement devices being developed to produce controlled thermonuclear fusion power. So, images, let's see what they look like. Wow. So you see like that all around. You see here? So it's a toroid like this. I guess they're inside. These people are inside of it here. It's pretty cool. Wow.
Professor,
Yeah.
it looks similar to one of like, I don't know, I watch a lot of movies. There was like an Avenger movie or something where all like the bad guys were stuck in something like that, and they would just run around in circles and would get confused because they would just end up in the same place again.
Yeah. I mean, I'm a huge movie buff, and sci-fi is, full of this kind of stuff. And a lot of times the sci-fi that we see, they will show the technologies that have not been developed yet, but they're on their way. So this is actually, though, it is in existence. It's not just a future technology. Wow, look at that. Spherical tokamak as model for next. So I guess that's a next generation tokamak. So what the idea for that is that for this one, they're going to confine the plasma in this area. So you see the magnetic field will push it that way, and then they confine it so they can actually make their own nuclear fusion, controlled fusion, so it won't get out of hand. I guess it's a Russian, the Russians are working on it. Tokamaks were initially conceptualized in the 1950s by Soviet physicists. Oh, Andrei Sakharov is very famous, one of the most famous physicists. The first tokamak began operation in 1958. Imagine that, like all the way back there. Wow. In 2019, JET remains the record holder for fusion output, reaching 16 megawatts of output for 24 megawatts of input heating power. That's pretty efficient. 16 out of 24. That's 67% efficiency. Wow. So you can go read up more. They give you the whole history. Oh, wow, the design. It's beautiful. Okay, cool. So, so you can kind of see it could be in a very small setting, like a tape recorder, versus, and then also something as big as a nuclear fusion. Okay, now let's go to the wire then. Any